This question involves air flowing through this circular tube. We know it enters at 20 degrees Celsius. We know surface temperature is remained at a constant temperature of 160 degrees Celsius. We want to find TE. So again, constant surface temperature. We know two of the temperatures among TI, TE, and TS. We want the third one. So which question comes to your mind first? Yes, it is this equation again. We know in this equation, this AS is the area of the surface which is exposed to convection. So it is not pi d squared over 4, it is pi dl. And m, mass flow rate, we know the velocity. So mass flow rate is density multiplied by volumetric flow rate. And volumetric flow rate is velocity multiplied by cross-sectional area, pi d squared over 4. And this Cp should be evaluated at 50 degrees Celsius, which is provided by the question. So we find Cp for air at 50 degrees Celsius from table 8-15. Ts is provided, Ti is provided. Now the only unknown is the convection coefficient. So again, to determine the convection coefficient, we need to find the appropriate correlation. To find the appropriate correlation, we need to determine its laminar turbulent. It's hydrodynamically developed or developing. It's thermally developing or developed. Now let's compute Reynolds number. Vd over mu, this is kinematic viscosity. And kinematic viscosity, this could be found from table 8-15 at 50 degrees Celsius. So we find this is smaller than 2300. So we know this is laminar flow. Now let's check hydrodynamically it's developed or not. Let's compute the hydrodynamic entry length for laminar flow. It is larger than the length of the plate. So this means it is hydrodynamically developing. So it requires 34 centimeters for the flow to be hydrodynamically developed. And the length of the tube is only 10 centimeters. So the flow did not get enough time to be hydrodynamically developed. Now let's compute the thermal entry length of this laminar flow. We find it is also larger than the length of the tube. So this means the flow is thermally developing. So it's hydrodynamically developing and thermally developing. Which correlation should we use? Let's check Prandtl number. Prandtl number for air at 50 degrees Celsius from table 8-15, we can find it. And it's smaller than 5. So which correlation should we use? Remember, for this problem, it is hydrodynamically developing and thermally developing. We won't be able to use this first correlation if Prandtl number was larger than 5. However, in this question, Prandtl number was smaller than 5, so we cannot use the first correlation, but we could use this one. Note, all properties are evaluated at the bulk mean fluid temperature, except for this mu s. So let's write the correlation. From the table for air, we know mu B is evaluated at the bulk mean temperature, which is 50 degrees Celsius. And this mu S is evaluated at surface temperature, which is 160 degrees Celsius. And plug in numbers, we can find Nusselt number. Then we can compute the convection coefficient. And again, this K is thermal conductivity of air, which should be evaluated at 50 degrees Celsius. So then we can compute convection coefficient. Now, all the properties in this formula is known. We can compute TE. This question involves liquid glycerin flows through these two parallel plates. We know Ti, we know Ts, we want to find Te. So again, surface temperature is constant. We know 2 of the 3 temperatures, we want the third one. So which equation should we use? Yes, it is the same equation. In this equation, Ts is known, which is 40 degrees Celsius. Ti is known, it is 25 degrees Celsius. And again, this As, remember As is the area of the surface which is exposed to convection. Since convection occurs between the fluid and the 2 plates, so As is the area of the 2 plates. About this Cp, the question states, evaluate the properties at 30 degrees Celsius. Is this a good assumption? First, let's try to evaluate the properties at 30 degrees Celsius, then determine if it's a good assumption. If it's not a good assumption, we just try another different temperature. So Cp at 30 degrees Celsius from table A13. Now the OD unknown is this H. So again, we need to determine Reynolds number. Note, this is very important. How do we determine Reynolds number for a non-circular plate? Reynolds number, you know, is Vd over mu. For a non-circular plate, we need to use this hydraulic diameter. And this kinematic viscosity, it is dynamic viscosity divided by density. Density multiplied by velocity, you know, it's mass flow rate divided by cross-sectional area. And this hydraulic diameter, it is 4 times of cross-sectional surface divided by the perimeter of the cross-sectional surface. So here AC and AC cancels out. This becomes 4 times of mass flow rate divided by P, which is the perimeter, and this mu, dynamic viscosity. So what is this P? Again, both P and AC, they're of the cross-sectional surface. So this is the cross-sectional surface. So P is 2 times of 1 plus 0.0125. So note, these two plates are apart by 2.5 millimeters. So this is 0.0125 meters. So now we can compute Reynolds number. 4 times of the mass flow rate, the mass flow rate is provided. This is the perimeter. Dynamic viscosity. So we find this is smaller than 2300. So we know it is laminar flow. Now let's decide if it's hydrodynamically developed or developing, if it's thermally developed or developing. So first let's compute hydrodynamic entry length for this laminar flow. And please pay attention here. Since it's non-circular, so here it should be the hydraulic diameter, dH. The hydraulic diameter, again, it is 4 cross-sectional area divided by perimeter. And the cross-sectional area AC is 1 by 2.5 millimeters. So we can find dH is this much. Then the hydrodynamic entry length. We find it's much smaller than the length of the plate. So this means the flow is hydrodynamically developed. Now let's compute the thermal entry length of this laminar flow. So again, this should be the hydraulic diameter. We find the thermal entry length is larger than the length of the plate. This means the flow is still thermally developing. Since it takes about 15 meters for the flow to be thermally developed, the plate is only 10 meters long, so the flow did not get the chance to be thermally developed. So the flow is hydrodynamically developed, but still thermally developing. So which correlation should we use? Let's go back to the slide. Remember, it is hydrodynamically developed, thermally developing, and it's laminar flow. So it's developing laminar flow. This is flow between isothermal parallel plates. So we should use this correlation. Plug in numbers, and from here we can find the convection coefficient. So note again, this D should be the hydraulic diameter, and this K should be the thermal conductivity of glycerin at 30 degrees Celsius. So now we have H. We can use this equation to find TE. Again, we have already had AS and all the other properties. So we plug in numbers, we find TE is 35.12 degrees Celsius. Remember, we started from the evaluation of the properties at 30 degrees Celsius. We need to know if this is a good assumption. So now we have TE, we can find the bulk mean temperature, which is the average between the entrance temperature and the exit temperature. So the entrance temperature is 25 degrees Celsius. Now we computed the exit temperature is 35. So the average is about 30 degrees Celsius. So we know 30 degrees Celsius is actually an appropriate temperature for evaluating the properties of glycerin. If we ended up with a bulk mean temperature which is much different from 30 degrees Celsius, that would mean evaluating the properties at 30 degrees Celsius was not appropriate. And also we need to find the heat transfer rate. So we know the glycerin enters at 25 degrees Celsius, it leaves at 35 degrees Celsius. So we know the temperature change experienced by the glycerin. So we can calculate the heat rate by Cm delta T.